Today we are going to start about one of the most important chapter of mechanics, that is called a simple harmonic motion. The chapter have a lot of importance in the field of IITJ because in IITJ examination we are going to get sure one question from this chapter. Or the main thing is that to read this chapter is very important because we can't directly get question from simple harmonic motion, but we are going to get the question in another form. Suppose we are in electrostat or in magnetostat, and if you go to the some wave mechanics, in many chapter we are going to get indirect question from this chapter. Suppose you're dealing in fluid mechanics. So in fluid mechanics, if there is some kind of oscillatory type of things, then we have to solve this using the concept of simple harmonic motion. So the chapter is very important for ITJ perspective, and this chapter requires uh, more understanding of mechanics. Like you have to apply the more concept of kinematics, dynamics. So at first you have to read all the chapter about power energy. So to come the chapter, because the chapter will cover whole the entire concept of mechanics. So so now our chapter will start. The main thing is that the simple harmonic motion is very important because in our surrounding there are a lot of things which is basically oscillatory in nature. Like what I'm speaking. So my sound wave is also in the form of some oscillatory thing. The medium particle will oscillate now its own position or mean position or to and from motion. When we go to the chapter sound wave, then we will understand that the particle the medium particle is also performing some kind of oscillation. So in the form of oscillation the sound wave propagate. When you go to the chapter of wave, to understand whole the wave theory, the simple harmonic motion is very crucial. So if you go to electrostat, then some charge will be start performing oscillatory motion, then you have to think about simple harmonic motion. So great importance. Now to understand simple harmonic motion, at first we have to understand two kind of things, two kind of basic terms. So at first we will discuss the basic terms that is going to use in simple harmonic motion. So first term is called as periodic motion. What is this periodic motion? So so what is this periodic motion? Periodic motion is basically some kind of motion in which the path and time of the particle is going to remain fixed. So like this, what we are talking about periodic motion. It is a kind of motion in which the path of particle is going to remain fixed, and the time, if we speak precisely, the time period, and then the time period of particle is going to remain fixed. As example, suppose you have example, the motion of, suppose this is nothing but sun, and this is earth. So earth is rotating around the sun in a circular fashion, circular kind of thing. And when you know that the time period is nothing but 365 days, or what is 1 year. The path of the particle around this the path of the particle path around the sun is in circular motion. So path is fixed, and the fixed path is in circle, and the time period is known as 365 days. So this kind of motion is basically known as periodic motion, or the motion of satellites. Example of periodic motion, the motion of planetary motion. They all kind of periodic motion because they have fixed path and they fixed time. Now, to understand, here we have discussed some term known as time period. What is known as time period? So I will try to understand what is time period. So at first we will discuss time period. Now time period is that a minimum interval of time. After that, the particle will going to repeat its position or its position. Or we're going to say, if it is going to repeat its position, then the velocity of the particle at time t plus t will be same, and the acceleration of particle after the time t will going to same. Like this fashion we are going to say, suppose you are going to define the time period in mathematical format. That means the the position of particle after time t must be equal to the position of particle at time t. So time period is nothing but, in simple manner we can say, the minimum time, or we can Now, what is time period? We're going to see that time period is a minimum time after which a particle is going to repeat its position. So this is the kind of thing. If you define time period as a mathematically term, then the after time t, we're going to see that the particle repeats its position. Now, after that, we have to see one more basic term that is called as frequency. What is frequency? Frequency is defined as the number of cycles per second, the unit, the cycle per second, or basically the number of revolution per second. Suppose in 1 second, the particle is completing 5 revolution. And that means its frequency is going to be is 5 revolution per second. Or the assign it if you are talking about the frequency of it is basically hertz, or we're going to call it cycle per second. So in 1 second, it is completing how much cycle? This is known as frequency. Okay. Now you understand some periodic motion, that is a path of particle is going to fixed and the time period of particle is going to fixed, and we are going to and we have seen some examples, that is satellite motion, planetary motion. Now we are going to proceed to our next one more basic definition, that is oscillatory motion. This is the main task of our this chapter, that is oscillatory motion. So what is oscillatory motion? Oscillatory motion is just some kind of to and fro motion of a particle about a fixed point. About a fixed point. Now the definition of this fixed point is so important. What is suppose I'm going to illustrate this with the help of example. Suppose this is a kind of thing, and this is a fixed point. There are a lot of name of this fixed point. I'm going to explain it in detail. So the particle is performing this like oscillator was like to and fro motion. Suppose particle is going like this and coming this. The most important thing is that in oscillatory motion, the extreme of particle is not necessary to be fixed. That is I'm going to tell that the extreme position not necessary to be same, because if when you proceed further, then we are going to learn about damped oscillation. So in damped oscillation, we are going to see that the extreme position of particle is not going to same. So the thing is that, so in oscillatory motion, it is a kind of to and fro motion about a fixed point, and extreme position should not be the same. Then there is one special case that you are going to read in this chapter, that is simple harmonic motion. In simple harmonic motion, the extreme position of particle is going to remain fixed. Suppose, and this extreme position is we are going to define as amplitude. There is a plus a and minus a. Suppose this is a particle. This is a fixed point, and about this point, the particle start oscillating. Now the particle have a fixed position, and this fixed position is not changing with time. So in that case, we are going to consider that the total mechanical energy of the system is going to remain conserved in this kind of motion. Without if there is Because if there is some kind of leaking force like a resistive force and some kind of force, then the energy of particle is going to leak. So it is going to lose its path. So the particle is maintaining its path. That means the total mechanical energy of the particle is going to remain conserved. And this kind of motion we are going to study in this chapter, known as simple harmonic motion or SHM. And we can say that here we will see that the path and time both are fixed. So we can say SHM as a periodic motion. Periodic motion. So this is the thing. Now I'm going to give some figure of this. Suppose this is spring having mass m. If you stretch this mass m little bit and left from that position, then this particle is going to oscillate about this position, like in this fashion. Suppose we have example. In above three example, we have seen the particle is oscillating about some point over, and we said this point as a fixed point, but this is not a true thing. It is not a true point. So basically, or it is not a true kind of thing. If you talk in terms of physics or if some physical point, then we are going to say this fixed point as a mean position. So there are a lot of mean position or something called as center of oscillation. There are a lot of name of this point, or we can say this as equilibrium position. These are names of this point. So our aim is to understand this mean position or this equilibrium position, because without the knowledge of this point we can't going to understand the SHM. So at first at first we heard about this equilibrium position or equilibrium position point in work power energy. So what is equilibrium? At first this thing comes in the mind. What is equilibrium? So equilibrium can be two kind of, there are two kind of equilibrium. One is basically called as rotational kind of equilibrium, rotational equilibrium, and second is translational equilibrium. So in rotational equilibrium, the net torque acting on the system must be zero. And if you're talking about translational equilibrium, then the net force acting on the system must be zero. So if we so about rotational equilibrium, when we are going to learn about angular SHM, then we are going to learn about rotational motion or rotational equilibrium. And when we are going to about linear SHM, then we are going to deal with net force sometimes zero, net force equal to zero. The Whenever there is a angular motion, then we need rotational equilibrium concept. So a system is in equilibrium if if a system is said to be in equilibrium if it is in rotational equilibrium plus translational equilibrium, then the system is going to say remain in the both equilibrium. So this thing is good. So the main thing is about that the part and if you classify the equilibrium, then we are going to classify the equilibrium in three parts. We learn this thing in work power energy. First kind of equilibrium is known as stable equilibrium, and second is nothing but unstable equilibrium, and third is neutral. Now the main thing is that we are understanding this because in every a particle is in uh, particle can be in three states. It may be in a stable equilibrium, or it may be in unstable equilibrium, or it may be in neutral equilibrium. But the thing is that in every state, particle is not going to perform oscillatory motion, because if you plot the stable equilibrium, the curve will like something like this. If you plot the unstable equilibrium curve, then it will like something, and in neutral equilibrium like this. Suppose if you are going to leave the particle from this position, then in a stable equilibrium position, if you basically throw the particle there, then the particle is going to come back to the mean position. But in this case, if you throw the particle, then particle will go and never come back. And if in this position, if you slightly push the particle, then particle is not going to come back. So in a stable equilibrium and neutral equilibrium, particle is not going to perform any kind of oscillatory motion. So the particle is going to perform oscillatory motion only under the stable equilibrium position. So our main concern is stable equilibrium position. What is a stable equilibrium position? We are going to understand, and from that we can conclude some more things. So, what is a stable equilibrium? Main aim is to understand what is a stable equilibrium position. So, like this. So what is a stable equilibrium position? So, what is a stable equilibrium? This is something like this. The particle, if you push slightly particle in this panel, then particle will try to turn towards the main position. If you drop the particle, if you push the particle in this panel, then particle will come back to this position. This position is known as stable equilibrium position. And we have seen that the if particularly so we have seen that the in a stable equilibrium position the net force on the system must be zero. So in the work power energy chapter we have learned that the net force is nothing but del U upon del x. We can define we can write the force in terms of potential, and this del U upon del x must be zero. That means if del U upon del x must be zero, then it implies that U should be minimum or U should be maximum. So there are two possibilities: the potential energy curve can be minimum or can be maximum. But from our intuition we have seen that if a particle have a minima at that position, or that it is going to a stable equilibrium. Otherwise, if it is maximum, then it can't perform oscillatory motion. So so the particle will perform oscillatory motion in such a potential in which basically the double derivative, if you are going to do double derivative of this thing, del 2 upon u upon del x square, then it is going to give the negative. That means it is minima at that point. So this is condition. So this is some kind of a condition to a potential. So if we have this kind of potential, then particle is going to perform oscillatory motion. Now, and, or we can draw this as a, if you draw u as a function of x, then this is a kind of thing, and this is some x equal to x naught. So now that now we are going to learn about simple harmonic motion. So at first we have to define one more thing, that is condition for oscillating motion. What is condition for oscillating motion? The main condition for oscillating motion is that the force should be directly proportional to minus of x. That means if you displace the particle in this direction, the force will always act uh, toward the fixed position or toward the mean position. So the force should be always opposite to the direction of position. Then we are going to get oscillatory motion. And this power, suppose if you generalize this case, then yes, then this power is basically going to in this pattern. This we can put some n type of things. So if you just remove this proportionally constant, then this will come. We are going to get force is minus kx to the power n some kind of thing. But if you think something in that, then we are going to get that for n equal to 0 2 4 6, that is for even integer, we are not going to get oscillatory motion. So if n is odd, like n is equal to 1 3, then we are going to get some kind of oscillatory motion. And this is the main condition. You can figure out this thing very easily, because if you are going to put 2 in that, then in that case, if our position is negative, then this whole term is going to be become positive. So the position is negative, that means the particle displace the particle in this fashion. So the force is positive. If you put square term, that means force is like in this manner. Sorry, the force will be in this manner, so particle is not going to come back. So if we have a even kind of terms like 0 2 4 6, then the particle is not going to perform oscillatory motion. So if n is equal to odd, and if n is equal to 1 3 4, so for n is equal to 1, for that case f is basically nothing but minus of kx, and this condition is known as simple harmonic motion. So by doing lots of steps, we finally come to this thing. But we have to understand things in deeply manner, then we're going to solve the questions. So so this is the main definition of simple harmonic motion, from where simple harmonic motion comes. And this is basically linear dependence, so that's why we are going to call as a simple harmonic motion. And we know that from here we can define acceleration like term also. We know that the net from Newton law, the net force acting on the system is mass times acceleration. So we can write this net force as a mass times acceleration, and this is nothing but kx. So from here we can say that acceleration is minus k upon mx. So k is also constant, m is also constant. So we can replace this k by m as a constant, something known as omega square. So acceleration is nothing but minus omega square kind of thing, this kind of thing. So the variance, what we are going to see, the acceleration is basically linearly dependent upon position. So if we plot this curve, and then we are going to get a, this is nothing but equation of a straight line with a negative slope, and this will be like this. This will be like this. We are going to get a, so what we have so what we have discussed till now is like this. So the curve of acceleration on x is going to, and this is negative slope because here is a negative sign. So and if you compute the slope, this is basically as a function of x, and this is some position that is known as a extreme position, that is plus a or minus a, you can say. And if you're going to compute the angle, this theta, or that is a slope angle, that is m, nothing but tan theta is going to give you omega square. So this is the linear dependence of acceleration of the position. So the main condition, if you are going to satisfy the acceleration, if a is negative of displacement, then in that case we are going to get the SHM. So when we are going to solve the problem, then our main aim is to satisfy this condition. SHM is minus of omega square x. Now we are going to understand the SHM and define some more basic terms related to this. So 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 we are getting f equal to minus kx, some kind of thing. Now this is mean position. We define mean position in great detail, and we are defining now the two positions, that is known as extreme position, plus a or minus a. What is this? Now what is this amplitude? We call this position as amplitude. We can define this amplitude as a many amplitude as a basically in a in a many fashion. So first thing we can define the amplitude as basically distance from the mean position, or we can define in like this, in this manner, that it is separation between mean position and equilibrium position. This separation is called as amplitude. Or we can also define this as basically this is half of the separation between the two extreme. Now this is certain kind of length, so this unit will be meter, or dimension will be length L. Now we are going to explain the, now we are going to understand the dynamics of simple harmonic motion, how the motion is basically occurring and how the motion is behaving in this thing. Suppose we have this kind of thing, and this is mean position, and this is plus a, and this is minus a. Now particle is basically going like this. Now we can see that whenever the, if we have seen the condition, that is force is minus of kx, that is force is always directed toward the mid position. So whenever particle is here, then force should be there. So what we are getting, that if our particle move here, then the force is always this. That means at this position if you come, then at this position the x is maximum. So at this position the force should be maximum. Or we know that the particle will just go there, and after that particle will turn. That means the velocity should be zero at this point. So this is a very important point. At extremum the velocity of the particle is going to zero. So the at extremum the velocity of the particle must be zero, and because particle has to turn back, and at and if particle turn back and moving towards the mean position, then force is also in that direction, and that means acceleration is in that direction. So the velocity of particle is going to increase. So when it comes at the mean position, then the velocity of the particle will be maximum. So at this, so that is the condition we have faced here. So velocity is 0 here, velocity is 0 here, and here velocity is maximum at mean position, and as I said, at mean position is 0. So now our aim is to, so the position and everything is, one more thing, most important thing is that in simple harmonic motion, the velocity, the position, the acceleration, all the thing is basically changing with time and position. So now our aim is to derive the relation for the position as a function of time, the displacement as a function, or displacement as a function of time, or velocity as a function of time, or acceleration as a function of time. We have a relation for acceleration as a function of x. We get that minus omega square, because we learn in kinematics that that if we have some position as a, if acceleration as a function of x, then we have to use the form like v dv upon dx to get velocity, some kind of thing. So now at first I'm going to basically derive the basic equations. So we conclude that the net force must be equal to mass time acceleration, and this and and this acceleration should be, we got that this acceleration is nothing but minus omega square x. So we can write this acceleration as a minus omega square x, and we know the acceleration is nothing but, if you write in terms of time, then this is dtx upon dt square, that is nothing but minus omega square x. Or we can write this as d2x upon dt square plus omega square x is 0. This is the basic equation of SHM, or this is the basic uh, second order differential equation of simple harmonic motion. But the solution of this equation is basically beyond the course of class 12 or ITG, so we are not going to solve this differential equation. So but at any cost, we are going to face this kind of a differential equation in sometimes in physics. So in that level, we have to remember the solution of that differential equation, or I'm going to derive this position by a different thing. But for, but for a but for a particular time, we can say that the if you solve this differential equation, then we are going to get term like something x equal to a sin omega t plus phi. This is the basically solution of this differential equation. Now I can derive this, but not mathematically, but by the using physics. So how we can derive this by physics? We are going to deal with this in in next session. The thing is that now I am giving a brief idea to how we are going to derive this. Now at first we know that we can write acceleration as a dv upon dx. That is nothing but minus omega square x. So from, if we solve from there, then we are going to get v is nothing but plus minus omega under root a square minus x square. This is basically our velocity. I'm going to derive this. This is basically EG integration. Then from this velocity, we can write this velocity as a dx upon dt. And from this, we are going x as a function of time t. This will be our approach to derive this. But it will come at many situations. So our aim is to just remember this differential equation. Okay. So thank you.